Welcome to aminacademy.com. In physics, let us discuss about elastic moduli of solids. Here, there are three types of stress and strain related to change in length, change in volume, and change in shape. Hence, we have three moduli of elasticity corresponding to each type we will discuss in terms of stress and strain. First, Young's modulus. The Young's modulus E is a property of the material that tells us how easily it can stretch and deform and is defined as the ratio of tensile stress sigma to a tensile strain E, where stress is the amount of force applied per unit area, stress equal to F by A, and strain is extension per unit length, that is delta L by L. Here, tensile strain equal to increase in length by original length, that is delta L by L. Tensile stress here central stress is applied force divided by area, that is force is mg over r pi r square here. Suppose it's a circular cross section. Then Young's modulus equal to tensile stress by tensile strain, that is y equal mg by pi r squared over delta by L by cross multiply. You will get y equal rearranging y equal mgl by pi r squared by dl. It's a Young's modulus formula. Here, Young's modulus further discussion. It is modulus of elasticity related to change in length of an object like a metal, wire, rod, beam, etc. due to the applied deforming forces. Hence, it is also called a elasticity of length. It is named after the British physicist Thomas Young. Consider a metal wire of length L having radius R suspended from a rigid support. A load mg is attached to the free end of the wire. Due to this, deforming force is applied to the free end of the wire in downward direction in its equilibrium position. Longitudinal stress is equal to applied force by area. We know that stress equal applied force by area, and forces we can write is mg by pi r square area. Then this is area. Now change in length by original stress, strain equal L by a change in length by original length. Now Young's modulus equal stress by strain, which is equal mg by pi r square mg by pi r square by L by L. By simplifying, we will get Young's modulus E R, we can write E equal mg L by mg L by pi r square. Next, here Young's modulus indicates the resistance of elastic solid to elongate or compression. This is the resistance to give elongation. That means any material have giving resistance when it is loaded to deform. Next one, bulk modulus. Bulk modulus K or B of a substance is a measure of the resistance of a substance to compression. It is defined as the ratio of infinitesimal pressure increase to the resulting relative decrease of volume. Suppose here cubical volume is here. Suppose you are applying a equal force in all phases, so its volume is reduced because of the bulk stress. That is the stress given by the body. That is we are applying the force and the volume is somewhat reduced. Overcoming that resistive force, its volume is reducing. Therefore, bulk modulus K equal to formula is minus V dP by dV, where K is a bulk modulus in Pascal, V equal to volume in meter cube, dP equal to pressure in Pascal, and dV equal to change in volume meter cube. This is the bulk modulus formula. Here, the bulk modulus is a modulus of elasticity. Also, it's called modulus of elasticity related to the change in volume of an object due to applied deforming forces. Hence, it is also called a elasticity of volume. Bulk modulus of elasticity is a property of solid, liquid, and gases. If a sphere made of a rubber is completely immersed in a liquid, it will be uniformly compressed from all sides. Suppose this compressive force is F, let the change in pressure on the sphere be dP and let the change in its volume be dV. If the original volume of the sphere is V, then the volume strain is change in volume by original volume, that is dV by V. The negative sign indicates that there is a decrease in volume. The magnitude of the volume strain is dV by dV, and volume stress by volume strain. Therefore, you can write this. Finally, you can get it. B dP by dV is the bulk modulus. Its dimension is, bulk modulus dimension is L over minus 1 M1 P square is minus square. Now, modulus of rigidity. Next is modulus of rigidity. Theta we can write. Here, shear modulus of an object is measure of the resistance of deformation when an external tangential force is applied to a plane of the object. Mathematically, it is expressed as the ratio of shear stress to shear strain. Shear modulus is denoted by D, capital D, sometimes S or mu. Another term used for shear modulus is modulus of rigidity. Here, shear modulus or modulus of rigidity denoted by G or sometimes S or mu we discussed is a measure of elastic shear stiffness of a material and is defined as the ratio of shear stress to the shear strain. Look at here. Shear stress is shearing force by area under shear, that is F by A. Shear strain is the relative displacement of any layer, its distance from a fixed layer. That is shear strain equal tan theta. Tan theta is very small, then we can use theta with this x by h. This is x and the height is h. Opposite by hypotenuse. The opposite by adjacent is tan theta. Now modulus of rigidity you can write stress by strain by, that is shear strain, that is equal to eta equal to F by A by theta, that is F over A theta, which is equal to FH by AX. This is an expression for the modulus of rigidity. That is, modulus of rigidity is FH by AX. X is the small distance sheared here, and H is the height from the floor to the force applied distance. A equal to cross area of that object. Now, The modulus of elasticity related to change in shape of an object is called rigidity modulus. It is the property of solids only as they alone possess a definite shape. Here, this is the modulus of rigidity is formula we have. Note this formula Fh by Ax. Next, Poisson ratio. Poisson ratio is the ratio of transverse contraction strain to longitudinal extension strain in the direction of the stretching force. Look at here. Suppose here it is tensile force is applied. Due to the tensile force, this contraction happen in the cross-sectional area. Tensile deformation is considered positive and compressive deformation is considered as negative. Therefore, suppose it's pulled, one side is compression, one side is tension. The definition of Poisson ratio contains a minus sign so that the normal materials have a positive ratio. Poisson's ratio, also called Poisson ratio or the Poisson coefficient or called coefficient de Poisson, is usually represented as a lowercase Greek letter nu. Now further discussion of the Poisson ratio here. Suppose a wire is fixed at one end and a force is applied to its free end. What happened? So that it's the wire gets stretched. Length of the wire increases and at the same time the diameter decreases. The wire becomes longer and thinner because its length is increased and cross section is reduced. If an equal and opposite forces are applied to an object along its length inward, the object gets compressed. There is a decrease in dimension along its length, and at the same time there is an increase in its dimension perpendicular to the length. Suppose if it's compressive force is applied, so the length reduced and cross section increased. The ratio of change in dimension to original dimension is the direction of the applied force is called the linear strain, while the ratio of the change in dimension to original dimension in a direction perpendicular to the applied force is called the lateral strain. Therefore, we can say Poisson ratio, we can get the Poisson ratio like lateral strain by linear strain. From this we can write d by d, that is cross-sectional areas dimension, that is diameter, then L by L, length by change in length by original length. Then we can write simplification. This is equal dl by dl. Poisson ratio has no unit since it have the ratio of the same units. So far we discussed about moduli of elastic modulus of the solids, that is Young's modulus and bulk modulus, modulus of rigidity, as well the Poisson ratio. We have done. Please subscribe our YouTube channel.